Okay, so first thing I want you guys to review is about the syllabus. You have my name, you have my email, and you have my online office hour here. So if you look on the announcement, you will see I have the office hour here, and in that I have the link for the Zoom meeting here. So whenever you want to meet me on the office hour from the 9 to the 11 a.m. on Monday and Wednesday, you can go to the Zoom meeting here. And if you have any question related to the class, to the course, or if you need my help for the homework or assignment, you are welcome to join the Zoom meeting on my office hour here. And you don't have to wait until the office hour. If you have any question, you can email me. So mostly I have a time to reply you shortly. Okay, so now come back to the syllabus here. Here's my instructor supervisor information. If you want to do anything with escalation, you can escalate it here. And you have some information about the disability, Ivytech online, something like that. For this class, you are required to have the book. You can buy it a physical book or electronic book here. So here's the name of the book. You have this one is the title. You have author here, edition, and you have ISBN here. So if you look on the announcement, the first thing that if you have not bought the book yet, you can try it for the free trial here. So for this class, you are allowed to use the first 3 chapters for free here. So you can go to the books and you can download a slide, PowerPoint slide for this class from here. Or if you want to use for book trial, you can go to the textbook free trial here. Okay, so from that you can search it to preload here, so, and you can add it. You can add it to the bookshelf, and you can use it for the 3 chapter for free here, for the first 3 chapter for free. And if you want to buy it electronic version, you can go to the announcement again, and it's that you can see the announcement for the required textbook here. So when you click on that and you follow the step I already instruct here, so you can follow the step to buy the book here. So you go to this one. You go to this one, you have to select your campus. You go to the Bloomington here. So when you go to Bloomington, you go to textbook here. Right? You go to the textbook here. You find the textbook. Okay, so first thing you have to select the campus. So for this one, you go to the Bloomington. This one is the term spring 2021. The department you have added here, software development here. And this one 120. Yes, 120 here. And this one you have 01N here. Okay, so you can click the find material for one course, and you see you have the option here. The first one, you can rent digital here. It's about 30 bucks, and if you want to buy it, it's about 50 bucks here. Okay, so that's everything about the textbook required for this class here. Now we come back to the syllabus. Do you have any questions so far? Let me know. Hello, any question?
No questions for me. I'm good.
Okay. So that's everything about the textbook. And you have also outline record here. And one thing about this one is the virtual instruction learning course via the Zoom meeting. So you guys are required to join the class virtually on the Zoom meeting from the 10 to the 12:50 p.m. on Tuesday and Thursday here. And for each week, you will have the assignment, right? So if you want to see what is the due date for the class here, you can go to the calendar and you can see what is the due date for the class here. And so mostly, okay, so I come back to the syllabus here. Okay, so basically every assignment or every homework, they have the due dates and you are supposed to submit it before the due date. If for any reason you are not able to submit before the due date, you have to seek a pre-approval from me. You have to send me the email and you need my pre-approval before for the any late submission here. And you have attendance drop deadline here. It's January 25th, and you have last day to withdraw is February 27 here. Okay. So here's some information about assignment and grading, and that's how graded work here. So you have the 6 discussion here. You have quizzes, you have checkpoint, you have assignment, you have a grade, progress reports, final project, and final exam here. Okay, so that's everything about the syllabus, everything about the textbook, everything about my office hour. So if you have any questions, just let me know. If you not, you can go to the module here. So when you click into module, it's everything about this class here. So when you scroll down, you work based on module here. So the first week, module 1, the second week, module 2, and so on here. So if you look on the module, you have the information about each of the module. The first thing is about the reading assignment here. So when you click on the reading assignment, they tell you what you are expected to do with the reading assignment. So for the first one here, you're supposed to read the chapter 0 and the chapter 1 in the book here. And some of the information here is customized by me. So we can look on the video YouTube here, you know how to work with the chapter here. Okay. First one, the reading assignment. And if you scroll down, you have some of the assignment or homework here. You have the discussion, you have quizzes, you have homework assignment, and some of the assignment. So one thing about the discussion here, so basically for every discussion, you have 2 due dates here. For every discussion, basically you have the 2 due dates. The first one, I will make the announcement. I made the announcement already, right? Here. So for every discussion, you have 2 due dates here. You have 2 due dates for every discussion. The first one is on Thursday, and the second one is on the Sunday here. And for the first one, you are supposed to post your initial before this due date. And for the second one, you are supposed to respond to at least 2 other students here. Okay. So now I go back to the module here. Any questions so far? Let me know.
Good.
Thank you.
I'm all right.
Okay. Okay, so now we go to the chapter 1, everything about the introduction here. We go a little bit a brief history of the computer and what's the computer. The computer is a mechanical electronic device. It stores, retrieve, and manipulate large amount of information at high speed, and it great accuracy here. So that's the thing here. You see, it all has high speed and great accuracy here, and it does not. It don't need any human intervention, and it carries out the instruction from the program here. We study what is the program later on this class here. So let me link to the. What is it?
Today, computers are all around us. From desktop computers to smartphones, they are changing the way that we live our lives. But have you ever asked yourself, what exactly is a computer? A computer is an electronic device that manipulates information or data. The computer sees data as ones and zeros, but Today, computers are all around us. From desktop computers to smartphones, they are changing the way that we live our lives. But have you ever asked yourself, what exactly is a computer? A computer is an electronic device that manipulates information or data. The computer sees data as ones and zeros, but it knows how to combine them into more complex things, such as a photograph, a movie, a website, a game, and much more. Computers use a combination of hardware and software. Hardware is any physical part of the computer, which includes all of the internal components and also the external parts like the monitor and the keyboard. Software is any set of instructions that tells the hardware what to do, such as a web browser, media player, or word processor. Now, when most people say computer, they're talking about a personal computer. This can be a desktop computer or a laptop computer, which has basically the same capabilities, but in a more portable package. Personal computers come in two main styles, PC and Mac. PCs are the most common type. There are many different companies that make them, and they usually come with the Microsoft Windows operating system. Macs, or Macintosh computers, are all made by one company, Apple, and they come with the Mac OS X operating system. Computers come in many other shapes and sizes. Mobile phones, tablets, game consoles, and even TVs have built-in computers, although they may not do everything a desktop or a laptop can. There's another type of computer that plays an important role in our lives, servers. A server serves information to other computers on a network. In fact, every time you use the internet, web servers deliver the web pages that you want to see to your computer. Servers are also used in many offices to store and share files. As you can see, there are many different types of computers out there, and they affect our lives in a variety of ways.
Okay, so we go to the history of computer. Actually, the computer have a long history. Is that you have some of the pioneer here. Some information about the pioneer. I don't want to go into detail for that. Okay, so we have the early computer in the 1940, the 1950. That is the first generation of computer. So you know that for every computer, the processing everything working is a binary. It's a binary here. The reason it working is binary because it processing everything with the 0 and 1, 0 and 1. And the reason that only working is 0 and 1 because every computer, every CPU, they work with multiple switches here. Yeah, right. So whenever you think about the switch, when you have the switch on, you have number 1, and you have the switch off, you have number 0 here. And by using combination of multiple 0 and 1, you can generate the picture, you can generate the word file, or you can working with the movie here. So for the first generation of computer, they use a vacuum tube to do the internal switching need for the computation here, and when you're working with the vacuum tube here, it have the huge size. It have very huge size. That's why for the first generation computer, you think about it like the building here. You have the like building. And in the 1955, you have about 300 in the world based on the vacuum tube here. So when we move to the 1950s, the invention of the transistor here is one of the most important invention on the 20th century here. So they replace the vacuum tube with the transistor here. So when the computer based on the transistor, they are the first solid state computer, and of course they need a climate control environment here. And when we move to the 1970s, you come with the idea of the personal computer, because you think that before that, every computer, it has the size of the building. It cannot be personal computer, right? So the personal computer only come into the light only when they have the invention of the microchip here. Now that you think about, you have the Intel, you have the AMD chip here, right? So in the 1974, the microchip along with the invention of microprocessor here. So they lead to creation of the first personal computer here. And you have the two pioneers, you have the Bill Gates and you have Steve Jobs here. And here is you have the information. Sorry, you have the picture of the vehicle. You have transistor and you have microchip here. So we have the. You think about you have vacuum tube here. You have the transistor here, and now we come with the microchip or microprocessor here. Okay, so when we think about the computer today, you have the supercomputer. It's very, very powerful and specialized, and for the massive, you have the massive computing problem by the big corporation and the government department here. And you have the mainframe that's used in the large corporation. And when you come to the personal computer, you have desktop computer, the laptop here. You have the PC that they're working with the Microsoft Windows operating system. And when you work with the Mac, you have OS here, right? Mac OS operating system here. And nowadays, even that you can use a smartphone and tablet as they are the computer also. Okay, so when you have a computer, you are able to interconnect them together. Right? Nowadays, you are not a personal computer, but you're able to communicate to everyone, to everywhere on the internet here. That's a time to the internet. Internet, it has the internet and the net here. That means you interconnect a million of network together here. Right? So based on internet, you can use the email, or you can use the World Wide Web here, and you can use them for the social networking also. Right? And now we move to the computer basics, and we talk about the component of computer. So basically, for the computer, you have the central processing unit. That is the brain of the computer here. It's the brain of the computer. You think about, you heard about the Intel CPU. You heard about the IBM CPU here. And is that you have the internal memory. It can have the RAM, or it can be ROM. You have mass storage device. It can be in the magnetic, optical, or solid state, and the cloud here. So basically, you have the system unit. The system unit is how for the CPU, for the internal memory, and for the most of the mass memory storage here. And you have the input device, the input device, everything that you bring in information into computer. It can be the keyboard, it can be the mouse, or something else, right? And for the output device, that means when you deliver inputs information to the computer do everything is the processing, and so lastly that just the bring out information, right? So you have the output device, you can have a monitor or printer or something like that. Okay, so let's watch a short video about the component of the computer here.
Show me the one whose safety deemed such destruction.
Okay, so basically for a computer, you have something about the input, right? You have input, you deliver the input. After that, the computer do everything with the processing here, and deliver out the output here, right? So you think about the input, you have the everything. You deliver information into the computer. You have the keyboard, you have the mouse, you have the barcode scanning, something like that, right? So processing, everything that computer do with the processing based on the inputs. So when it's done with the processing, it deliver the output here. The output you think about, you have the monitor here, you have the speaker, you have the printer, something like that. Right? So for the computer, you have the two parts. You have the the first one, the hardware, and the second one, the software here. Right. So basically, for the hardware, you have everything about the input. You have the system unit, and you have the output here. Okay. So the CPU is the core, is the brain of the computer here. That it receives the program instruction. It receives the program instruction. You perform everything with the calculation here. And when working with the calculation, it can be the arithmetic or logical operation here, and it control other computer component here. So basically for the CPU, it consists of millions of transistors and in a single microchip here. And when you plug into the motherboard here, and the speed of the CPU is in the hertz here, right? It's a hertz, so we can think about the 3 gigahertz or 4 gigahertz or something like that. So hertz is one of the fluctuation here, right? So for every 1 hertz, that means able to do it's one processing calculation here. So when I think about gigahertz, that means you have billion here, right? You have billion. You think about you have mega, that means you have million, and for the giga you have billion. So when you think about, you have the CPU, when you have a CPU of 3 gigahertz here, so that means is that CPU here able to do with the 3 billion calculation per second here. So think about in one second it's able to do processing for the 3 billion calculation here, processing calculation here. And basically for the system unit, you have motherboard, right? So in the motherboard, you have the CPU, you have the RAM, and you have ROM, and you have storage also. You have the storage. CPU is, you know, that it's a brain of the computer, everything with the calculation here, processing here, right? For the RAM, it's a random access memory. So we think about it's a crash pad for use and see or the work here. It can be read from or written to, and normally it's measured in the megabyte or gigabyte here. So think about, when you think about the RAM, it's a random access memory. That means it's only temporary here. So when you think about when you access the RAM, when you turn off the computer, everything gone from the RAM here. And the second one is the ROM. ROM is a read-only memory. It's normally a content instruction used by computer during startup here. So normally when you power on the computer, the ROM is the one who control everything about the hardware, and it interface with the hardware and to make sure that the hardware working smoothly here. Right? You think about that. And it can think about the ROM, it's a reference sheet and cannot be entered by the computer user here. Okay, but for it's a reverse RAM, it's a random temporary access memory. Right? And for the system unit, you also have the storage. Storage, you can have the hard disk drive, or nowadays a lot of you use the SSD here, solid state drive here. So now talking about the basic units of memory, you have the 1 bit. You have 1 bit, that means you have 2 possibilities here, 0 and 1, 0 and 1 here for 1 bit. And you have 1 byte. 1 byte is normally consists of the 8 bit here. That's 8 bits is 1 byte. So you have 1 kilobyte, you have 1 megabyte, and you have 1 gigabyte and so. But normally you see that for the kilobyte, it's not 1,000 bytes here. Actually, you have the 2 raised to 10 bytes. That means it's 1,024 bytes, not 1,000 bytes here. The same with the megabyte. Megabyte is 1,024 kilobyte, and for the 1 gigabyte, it's 1,024 megabyte here. And the reason is 1024 because you went with 2, you rate to 10 here, you have 1024 here. Okay, so when we move to the mass storage device, it can be the HDD with the magnetic storage here. It can be optical storage. It can be solid state storage. And nowadays, a lot of you using the cloud computing here.
It's school. It's open. Imagine an airplane flying 1 millimeter above the ground and circling the Earth once every 25 seconds while counting every blade of grass. Shrink all that down so that it fits in the palm of your hand, and you'd have something equivalent to a modern hard drive, an object that can likely hold more information than your local library. So how does it store so much information in such a small space? At the heart of every hard drive is a stack of high-speed spinning disks with a recording head flying over each surface. Each disk is coated with a film of microscopic, magnetized metal grains, and your data doesn't live there in a form you can recognize. Instead, it is recorded as a magnetic pattern formed by groups of those tiny grains. In each group, also known as a bit, all of the grains have their magnetizations aligned in one of 2 possible states, which correspond to zeros and ones. Data is written onto the disk by converting strings of bits into electrical current fed through an electromagnet. This magnet generates a field strong enough to change the direction of the metal grain's magnetization. Once this information is written onto the disk, the drive uses a magnetic reader to turn it back into a useful form. Much like a phonograph needle translates a record's grooves into music. But how can you get so much information out of just zeros and ones? Well, by putting lots of them together. For example, a letter is represented in 1 byte, or 8 bits, and your average photo takes up several megabytes, each of which is 8 million bits. Because each bit must be written onto a physical area of the disk, we're always seeking to increase the disk's areal density, or how many bits can be squeezed into 1 square inch. The areal density of a modern hard drive is about 600 gigabits per square inch, 300 million times greater than that of IBM's first hard drive from 1957. This amazing advance in storage capacity wasn't just a matter of making everything smaller, but involved multiple innovations. A technique called the thin film lithography process allowed engineers to shrink the reader and writer. And despite its size, the reader became more sensitive by taking advantage of new discoveries in magnetic and quantum properties of matter. Bits could also be packed closer together thanks to mathematical algorithms that filter out noise from magnetic interference and find the most likely bit sequences from each chunk of readback signal. And thermal expansion control of the head, enabled by placing a heater under the magnetic writer, allowed it to fly less than 5 nanometers above the disk surface, about the width of 2 strands of DNA. For the past several decades, the exponential growth in computers' storage capacity and processing power has followed a pattern known as Moore's Law, which in 1975 predicted that information density would double every 2 years. But at around 100 gigabits per square inch, shrinking the magnetic grains further or cramming them closer together posed a new risk, called the superparamagnetic effect. When a magnetic grain volume is too small, its magnetization is easily disturbed by heat energy and can cause bits to switch unintentionally, leading to data loss. Scientists resolved this limitation in a remarkably simple way by changing the direction of recording from longitudinal to perpendicular, allowing areal density to approach 1 terabit per square inch. Recently, the potential limit has been increased yet again through heat-assisted magnetic recording. This uses an even more thermally stable recording medium whose magnetic resistance is momentarily reduced
by heating up a particular spot with a laser and allowing data to be written. And while those drives are currently in the prototype stage, scientists already have the next potential trick up their sleeves: bit-patterned media, where bit locations are arranged in separate nano-sized structures, potentially allowing for areal densities of 20 terabits per square inch or more. So it's thanks to the combined efforts of generations of engineers, material scientists, and quantum physicists that this tool of incredible power and precision can spin in the palm of your hand.
Okay, so that we talk about the permanent storage, right? So basically you see that for the HDD or the SSD, they are permanent storage. That means think about when you have the word processing file here, you have think about word here. Right? So when you click to open it, actually it's stored in the, think about the word file here, it's stored in the HDD here, right? Hard disk drive here. And you have the word file here. So we open it, actually it pull all the information into the RAM here, into the RAM. The reason it pull all the information into the RAM because the RAM, it works with the high speed, right? The higher speed. And for HDD, it works at very, very low speed. If you think about the HDD, everything is working the physical spin here. It's spin around, and that's why it works at low speed here. For the RAM, it works at very, very high speed. But the thing when you load into the RAM, it's only temporary. Right, so you know that the RAM is only temporary. So that's why for everything, when we do with editing, when we do with the modification of the file, if you want to save it, you have to copy back it to the HDD here. So when you click the save, actually it sends information from the RAM to the HDD and it's stored into the HDD here. Okay, so you have a multiple way of storage device. It can be a magnetic device. It can be optical storage. You have the CD or DVD here. You have SSD. Nowadays, nowadays a lot of you working with SSD. It's working very, very fast, and you don't have a physical component of spinning here. That's why working very fast here. And one more thing nowadays is very flexible for you is the cloud computing. If you think about we're working with Google Drive, right? So you can store information everywhere, anytime. Right? So you don't have to stay at the home, or you don't have to go to the office to open the file. You can open it from anywhere, providing that you have the internet access here. And you move to the inputs and outputs. Think about that. For every computer, you will have the 3 components here. You have input, you have processing here, and you have output here. All right. Input, you put information into the computer here. You give information in the computer. It can be the keyboard, it can be the mouse, it can be the digital pen here. When I write down here, right? Or it can be the touch screen, joystick, or voice command here. So when we get the input to the computer, everything working is the processing, and when working your processing, it delivers out the output here. Right? So the output, it can be the monitor, printer, speaker, or more here. So now we move to the software and programming language here. So basically, for the programming, for the software, they break it down into 2 major groups. The first one is the application software, and the second one is the system software here. For the application software, it enhances the productivity, it solves problems, it supplies information, and provides entertainment. And some of example, it can be the word processing, database manager, spreadsheet, photo editor, and browser here. And for the system software, the most common is the operating system. Right? So system software is everything about the control and maintain the hardware here. The interface with the hardware and control the hardware here. And also it's interface with the end user here. So you think about operating system, you think about the window, right? You think about window. In one side, it control every hardware component here. The second one, it interface with the user here, right? And it can manage and communicate with the application. And some of the example is a window. It can be host, Linux, Unix here. Let me show you. What is this? Okay, so for the programming, they break it down into the low level language and the high level language here. So I think it's better you watch this video here.
A program is a set of instructions that tells a computer what to do in order to come up with a solution to a particular problem. Programs are written using a programming language. A programming language is a formal language designed to communicate instructions to a computer. There are two major types of programming languages: low-level languages and high-level languages.
Okay, so that remember you have the two major category of the language. The first one, the low-level language, and the second one is the high-level language here.
Low-level languages are referred to as low because they are very close to how different hardware elements of a computer actually communicate with each other. Low-level languages are machine-oriented and require extensive knowledge of computer hardware and its configuration.
Okay, so for the low-level language, you remember that it's a machine-oriented and it requires intensive knowledge of the computer. That means you have to deeply understand every component, every hardware component of the computer. So you have to think about what is the keyboard it is, what is a monitor it is, something like that. Right? You only have to deeply understand of every hardware component of the computer here.
There are two categories of low-level languages: machine language and assembly language. Machine language, or machine code, is the only language that is directly understood by the computer, and it does not need to be translated. All instructions use binary notation and are written as a string of ones and zeros. A program instruction in machine language may look something like this. Technically speaking, this is the only language computer hardware understands. However, binary notation is very difficult for humans to understand. This is where assembly languages come in. An assembly language is the first step to improve programming structure and make machine language more readable by humans. An assembly language consists of a set of symbols and letters. A translator is required to translate the assembly language to machine language. This translator program is called the assembler. It can be called the second generation language since it no longer uses ones and zeros to write instructions, but terms like move, add, sub, and end. Many of the earliest computer programs were written in assembly languages. Most programmers today don't use assembly languages very often, but they're still used for applications like operating systems of electronic devices and technical applications, which use very precise timing or optimization of computer resources. While easier than machine code, assembly languages are still pretty difficult to understand. This is why high-level languages have been developed. A high-level language is a programming language that uses English and mathematical symbols, like plus, minus, percent, and many others, in its instructions. When using the term programming languages, most people are actually referring to high-level languages. High-level languages are the languages most often used by programmers to write programs. Examples of high-level languages are C++, Fortran, Java, and Python. To get a flavor of what a high-level language actually looks like, consider an ATM machine where someone wants to make a withdrawal of $100. This amount needs to be compared to the account balance to make sure there are enough funds. The instruction in a high-level computer language would look something like this. X equals 100. If balance less than X, print insufficient balance, else, print please take your money. This is not exactly how real people communicate, but it is much easier to follow than a series of ones and zeros in binary code. There are a number of advantages to high-level languages. The first advantage is that high-level languages are much closer to the logic of a human language. A high-level language uses a set of rules that dictate how words and symbols can be put together to form a program. Learning a high-level language is not unlike learning another human language. You need to learn vocabulary and grammar so you can make sentences. To learn a programming language, you need to learn commands, syntax, and logic, which correspond closely to vocabulary and grammar. The second advantage is that the code of most high-level languages is portable, and the same code can run on different hardware. Both machine code and assembly languages are hardware-specific and not portable. This means that the machine code used to run a program on one specific computer needs to be modified to run on another computer. Portable code in a high-level language can run on multiple computer systems without modification. However, modifications to code in high-level languages may be necessary because of the operating system. For example, programs written for Windows typically don't run on a Mac. A high-level language cannot be understood directly by a computer, and it needs to be translated into machine code. There are two ways to do this, and they are related to how the program is executed. A high-level language can be compiled or interpreted. A compiler is a computer program that translates a program written in a high-level language to the machine language of a computer. The high-level program is referred to as the source code. A typical computer program processes some type of input data to produce output data. The compiler is used to translate source code into machine code or compiled code. This does not yet use any of the input data. When the compiled code is executed, referred to as running the program processes the input data to produce the desired output. When using a compiler, the entire source code needs to be compiled before the program can be executed. The resulting machine code is typically a compiled file, such as a file with an exe extension. Once you have a compiled file, you can run the program over and over again without having to compile it again. If you have multiple inputs that require processing, you run the compiled code as many times as needed. An interpreter is a computer program that simulates a computer that understands a high-level language. This means the interpreter translates the source code line by line during execution. Consider again a computer program that processes some type of input data to produce output data. The interpreter executes the code line by line, which results in the desired output data. The only result is the output data. There is no compiled code. When using an interpreter, every time you want to run the program, you need to interpret the code again, line by line. There is no compiled code to use if you have multiple inputs that require processing. To understand the difference between compiling and interpreting, let's examine the equivalent in human languages. For example, consider a movie made in Asia where all the characters speak Vietnamese. To market the movie to an international audience, the spoken text needs to be translated into English. A translator would sit down and carefully translate all the text and create subtitles for the movie. Anytime someone wants to watch the movie, they can turn on the subtitles. This type of translation is the equivalent of compiling. Everything is translated once and can be used many times afterwards. Now consider a delegate from Vietnam giving a speech in the United Nations in Vietnamese. In order for the attendees to understand the speech, there are a number of translators who provide a translation that is transmitted to the attendees' headphones. This translation occurs close to real time. Every time the delegate speaks in Vietnamese, the translators get to work. This type of translation is the equivalent of interpreting. Text is translated line by line as necessary, and the results are not used again. Compiled code tends to be faster since the translation is completed in one step prior to the actual execution. Interpreted code, on the other hand, is more flexible and can be run interactively. For example, using interpreted code, you can try out a few lines to see if they work very quickly without having to go through the steps of compiling and executing the program. One advantage of using compiled code is that it does not reveal the original source code. This makes it possible to distribute a program without revealing its inner workings. When you install a software application on your computer, you are typically installing a compiled version of the code. You can run the software application, but you can't open up the source code in the original programming language. For many companies selling software applications, the original source code is a well-kept secret and gives them their competitive advantage over other companies. Examples of compiled languages include C and its derivative, C++ and C#, COBOL, and Fortran. Examples of interpreted languages are Java, Perl, Python, and Ruby. There are two major types of programming languages, low-level languages and high-level languages. Low-level languages are machine-oriented and require extensive knowledge of computer hardware and its configuration. There are two categories of low-level languages, machine language and assembly language. Machine language, or machine code, consists of binary code and is the only language that is directly understood by the computer. An assembly language consists of a set of symbols and letters and requires translation to machine language. Both machine code and assembly languages are hardware specific. A high-level language is a programming language that uses English and mathematical symbols in its instructions. To execute a program in a high-level language, it can be compiled or interpreted. A compiler translates the entire program written in a high-level language to a machine language prior to execution. An interpreter translates the program line by line during execution.
Okay, do we have any questions so far? Let me know. Any question? Okay.
Good.
Okay, so basically that review about the programming here. You have the two major categories here. The first one, the low level, right? You have a low level. And the second one, you have high level here. So in the low level, again, they break it down into machine code here. Machine language, and you have the assembly here. And in the high level, you you can have a compiling. You have compiling and interpreting here. So when you compare between the low level and high level, the first thing is the low level. You have to deeply understanding of the hardware here. You have the extensive knowledge of the hardware, and it is a hardware specific. So when we talk about the hardware specific, that means you have to totally understanding and you have the extensive knowledge of the hardware here. And when working with hardware specific, that means when you do the coding for this computer, you are not able to do with the same with the other computer here because it is a hardware specific. You think about this computer, you have the Dell keyboard, right? Something like keyboard here, and the other computer you have the HP here, Hewlett Packard keyboard. So when working with the low level, when you developing the program, it only working with the Dell keyboard here. But when you move to the second computer with the HP keyboard here, it's not work because it is hardware specific here. Right? So the thing about when you think about the low level here, you have to know that you must have the deep, you must have the extensive knowledge of the hardware here. And when working the machine language, everything in 0 and 1, because you know that the underlying of every computing it is processing with the binary 0 and 1, right? So when working the machine language, everything is 0 and 1. So when working 0 and 1, it works very fast. You don't have to translate it. You don't have to interpret in machine language here, right? So and working the machine language here, it works very fast. It don't require anything with the memory to store about the compiling or interpreting here. It works very fast, but you have the trade-off here. It's very hard to do, right? You have to deeply understanding about the hardware specific here. So when you move to the assembly, a little bit improved from the machine language, a little bit improved from machine language. So it helps you a little bit easier to understand and to follow the coding here because it translates from 0 and 1 into the character here. A little bit. So the thing when you think about the low level here, you have machine language working everything with the 0 and 1, and you have the assembly. It works something about the character here. So when working the low level, it works very fast. It works very fast because it don't require anything with the compiling or translating here. But in the other end, you have to totally understand about the hardware specific here. And when you move to the high level language, it's very easy for you to follow and to study the language here. So I think about it's the same with the grammar here. I think about you add, your subtraction, do everything with that. For the high level language, it can be portable. That means when you have the high level language programming here, you can run from this computer and you can bring it to the another computer. You have no challenge for this because it works in the high level computer here, right? For the high level programming language, and they break it down into two categories. The first one is compiling, and the second one is interpreting here. The compiling, that means you have to, when you work in the program, you have to compile it into the machine language. And you just need to compile for one time only. So when you already compile it, you're able to do it for, you are able to use it for multiple times, right? So we are able to do it for multiple times. You think about the file exe file here. When you have the portable exe file, you're able to use it for multiple times. For interpreting, you have to interpreting every single line of the coding here, right? Every single line of the coding. So you think about, when you think about the compiling, you think about the subtitle here. You think about you see the movie, the subtitle of movie. So when you compiling the subtitle, you can use it for multiple times, again and again and again, right? For the interpreting, you think about you think about the meeting that when you want to interpreting from the someone speak the foreign language. So every you have to stop and interpreting to the English here, right? So when you compare between the low level and high level, this one it works very fast. It works very fast, but it requires you to totally understand of the hardware, and it's a hardware specific. That means for every computer you must have the customized programming here. It cannot bring from this programming to have it run into another computer here. For the high level, it works a little bit slower, right? Because you have to translate it, you have to compiling, you have to interpreting it. So it requires a little bit of the resources, memory here, right? And in the other hand, it's very easy for you to follow up, easy for you to understanding, and it is portable. That means you're able to run from the computer and you can bring it to the another computer here. And you think about this one, you have when you have the compiling, you can hide the source code, right? Because when you compile it translate into the exe here, the end user are not able to see anything with the source code here. Okay, so any question for this one? Let me know.
I'm all good.
Good.
Okay, so when you're writing program, normally you have, when working with a high level language, you need appropriate software. I think about you need to be working with the C++ or something, Python or something like that. You need a text editor to tie and edit the program. You have a debugger. So when you compiling, you see what is going on, what is something wrong with that. Right? So you have a compiler and interpreter to translate the program into the machine language, because every computer, at the end of every computer, in order to processing the data, they must work with the machine language. That's why for every program, you have to do with the compiling or the interpreting here. So we move to the programming logic. So all programming language can use a basic programming logic. If you understand this logic, it will be much easier to learn any specific language here. So you think about the logic. When you understand the logic, you can use it. You can use it working with the C++ or Python or Fortran. You have no challenging here, because when you understand the logic, you're able to apply it into specific language here. Let's see what you have for this one. Okay, this one. I think this one will be good one.
Hello world, I'm Carrie-Anne and welcome to Crash Course Computer Science. Over the course of this series, we're going to go from bits, bytes, transistors and logic gates all the way to operating systems, virtual reality and robots. We're going to cover, but just to clear things up, we are not going to teach you how to program. Instead, we're going to explore a range of computing topics as a discipline and a technology. Computers are the lifeblood of today's world. If they were to suddenly turn off all at once, the power grid would shut down, cars would crash, planes would fall, water treatment plants would stop, stock markets would freeze, trucks with food wouldn't know where to deliver, and employees wouldn't get paid. Even many non-computer objects like DFTBA shirts and the chair I'm sitting on are made in factories run by computers. Computing really has transformed nearly every aspect of our lives. And this isn't the first time we've seen this sort of technology-driven global change. Advances in manufacturing during the Industrial Revolution brought a new scale to human civilization in agriculture, industry, and domestic life. Mechanization meant superior harvests and more food, mass-produced goods, cheaper and faster travel and communication, and usually a better quality of life. And computing technology is doing the same right now, from automated farming and medical equipment to global telecommunications and educational opportunities. And new frontiers like virtual reality and self-driving cars. We are living in a time likely to be remembered as the electronic age. And with billions of transistors in just your smartphones, computers can seem pretty complicated. But really, they're simple machines that perform complex actions through many layers of abstraction. So in this series, we're going to break down those layers and build up from simple ones and zeros to logic units, CPUs, operating systems, the entire internet and beyond. And don't worry, in the same way someone buying t-shirts on a web page doesn't need to know how that web page was programmed, or the web designer doesn't need to know how all the packets are routed, or router engineers don't need to know about transistor logic, this series will build on previous episodes, but not be dependent on them. By the end of this series, I hope that you can better contextualize computing's role, both in your own life and society, and how humanity's arguably greatest invention is just in its infancy, with its biggest impact yet to come. But before we get into all that, we should start at computing's origins, because although electronic computers are relatively new, the need for computation is not. The earliest recognized device for computing was the abacus, invented in Mesopotamia around 2500 BCE. It's essentially a hand-operated calculator that helps add and subtract many numbers. It also stores the current state of the computation, much like your hard drive does today. The abacus was created because the scale of society had become greater than what a single person could keep and manipulate in their mind. There might be thousands of people in a village or tens of thousands of cattle. There are many variants of the abacus, but let's look at a really basic version, with each row representing a different power of 10. So each bead on the bottom row represents a single unit. In the next row, they represent 10, the row above, 100, and so on. Let's say we have 3 heads of cattle represented by 3 beads on the bottom row on the right side. If we were to buy 4 more cattle, we would just slide 4 more beads to the right for a total of 7. But if we were to add 5 more after the first 3, we would run out of beads. So we would slide everything back to the left, slide 1 bead on the second row to the right, representing 10, and then add the final 2 beads on the bottom row for a total of 12. This is particularly useful with large numbers. So if we were to add 1,251, we would just add 1 to the bottom row, 5 to the second row, 2 to the third row, and 1 to the fourth row. We don't have to add in our head, and the abacus stores the total for us. Over the next 4,000 years, humans developed all sorts of clever computing devices like the astrolabe, which enabled ships to calculate their latitude at sea, or the slide rule for assisting with multiplication and division. And there are literally hundreds of types of clocks created that could be used to calculate sunrise, tides, positions of celestial bodies, and even just the time. Each one of these devices made something that was previously laborious to calculate much faster, easier, and often more accurate. It lowered the barrier to entry and at the same time amplified our mental abilities. Take note, this is a theme we're going to touch on a lot in this series. As early computer pioneer Charles Babbage said, at each increase of knowledge, as well as on the contrivance of every new tool, human labor becomes abridged. However, none of these devices were called computers. The earliest documented use of the word computer is from 1613 in a book by Richard Braithwaite. And it wasn't a machine at all, it was a job title. Braithwaite said, "I have read the truest computer of times and the best arithmetician that ever breathed, and he reduceth by days into a short number." In those days, computer was a person who did calculations, sometimes with the help of machines, but often not. This job title persisted until the late 1800s, when the meaning of computer started shifting to refer to devices. And notable among these devices was the step reckoner built by German polymath Gottfried Leibniz in 1694. Leibniz said, "It is beneath the dignity of excellent men to waste their time in calculation when any peasant could do the work just as accurately with the aid of a machine." It worked kind of like the odometer in your car, which is really just a machine for adding up the number of miles your car has driven. The device had a series of gears that turned. Each gear had 10 teeth to represent the digits from 0 to 9. Whenever a gear bypassed 9, it rotated back to 0 and advanced the adjacent gear by 1 tooth. Kind of like when hitting 10 on that basic abacus. This worked in reverse when doing subtraction too. With some clever mechanical tricks, the step reckoner was also able to multiply and divide numbers. Multiplications and divisions are really just many additions and subtractions. For example, if we want to divide 17 by 5, we just subtract 5, then 5, then 5 again, and then we can't subtract any more 5s. So we know 5 goes into 17 3 times, with 2 left over. The step reckoner was able to do this in an automated way and was the first machine that could do all 4 of these operations. And this design was so successful, it was used for the next 3 centuries of calculator design. Unfortunately, even with mechanical calculators, most real-world problems required many steps of computation before an answer was determined. It could take hours or days to generate a single result. Also, these handcrafted machines were expensive and not accessible to most of the population. Before the 20th century, most people experienced computing through pre-computated tables, assembled by those amazing human computers we talked about. So if you needed to know the square root of 8,675,309, instead of spending all day hand cranking your step reckoner, you could look it up in a huge book full of square root tables in a minute or so. Speed and accuracy is particularly important on the battlefield, and so militaries were among the first to apply computing to complex problems. A particularly difficult problem is accurate firing artillery shells, which by the 1800s could travel well over a kilometre, or a bit more than half a mile. Add to this varying wind conditions, temperature, and atmospheric pressure, and even hitting something as large as a ship was difficult. Range tables were created that allowed gunners to look up environmental conditions and the distance they wanted to fire, and the table would tell them the angle to set the cannon. These range tables worked so well, they were used well into World War II. The problem was, if you changed the design of the cannon or of the shell, a whole new table had to be computed, which was massively time-consuming and inevitably led to errors. Charles Babbage acknowledged this problem in 1822 in a paper to the Royal Astronomical Society entitled Note on the Application of Machinery to the Computation of Astronomical and Mathematical Tables. Let's go to the thought bubble. Charles Babbage proposed a new mechanical device called the difference engine, a much more complex machine that could approximate polynomials. Polynomials describe the relationship between several variables, like range and air pressure, or amount of pizza Carrie-Anne eats and happiness. Polynomials could also be used to approximate logarithmic and trigonometric functions, which are a real hassle to calculate by hand. Babbage started construction in 1823, and over the next 2 decades tried to fabricate and assemble the 25,000 components collectively weighing around 15 tons. Unfortunately, the project was ultimately abandoned. But in 1991, historians finished constructing a difference engine based on Babbage's drawings and writings, and it worked. But more importantly, during construction of the difference engine, Babbage imagined an even more complex machine, the analytical engine. Unlike the difference engine, step reckoner, and all other computational devices before it, the analytical engine was a general-purpose computer. It could be used for many things, not just one particular computation. It could be given data and run operations in sequence. It had memory and even a primitive printer. Like the difference engine, it was ahead of its time, was never fully constructed. However, the idea of an automatic computer, one that could guide itself through a series of operations automatically, was a huge deal and would foreshadow computer programs. English mathematician Ada Lovelace wrote hypothetical programs for the analytical engine, saying a new, a vast, and a powerful language is developed for the future use of analysis. For her work, Ada is often considered the world's first programmer. The analytical engine would go on to inspire arguably the first generation of computer scientists, who incorporated many of Babbage's ideas in their machines. This is why Babbage is often considered the father of computing. Thanks, thought bubble. So by the end of the 19th century, computing devices were used for special purpose tasks in the sciences and engineering, but rarely seen in business, government, or domestic life. However, the US government faced a serious problem for its 1819 census that demanded the kind of efficiency that only computers could provide. The US Constitution requires that a census be conducted every 10 years for the purposes of distributing federal funds, representation in Congress, and good stuff like that. And by 1880, the US population was booming, mostly due to immigration. That census took 7 years to manually compile. And by the time it was completed, it was already out of date. And it was predicted that the 1819 census would take 13 years to compute. That's a little problematic when it's required every decade. The Census Bureau turned to Herman Hollerith, who built a tabulating machine. His machine was electromechanical. It used traditional mechanical systems for keeping count, like Leibniz's step reckoner, but coupled them with electrically powered components. Hollerith's machine used punch cards, which were paper cards with a grid of locations that could be punched out to represent data. For example, there was a series of holes for marital status. If you were married, you would punch out the married spot. Then when the card was inserted into Hollerith's machine, little metal pins would come down over the card. If a spot was punched out, a pin would pass through the hole in the paper and into a little vial of mercury, which completed the circuit. This now completed circuit powered an electric motor, which turned a gear to add one, in this case, to the married total. Hollerith's machine was roughly 10 times faster than manual tabulations, and the census was completed in just 2.5 years, saving the census office millions of dollars. Businesses began recognizing the value of computing and saw its potential to boost profits by improving labor and data-intensive tasks like accounting, insurance appraisals, and inventory management. To meet this demand, Hollerith founded the Tabulating Machine Company, which merged with other machine makers in 1924 to become the International Business Machines Corporation, or IBM. which you've probably heard of. These electromechanical business machines were a huge success, transforming commerce and government. And by the mid-1900s, the explosion in world population and the rise of globalized trade demanded even faster and more flexible tools for processing data, setting the stage for digital computers, which we'll talk about next week. Crash Course Computer Science is produced in association with PBS Digital Studios. At their channel, you can check out a playlist of shows like PBS Idea Channel, Physics Girl, and It's Okay to Be Smart. This episode was filmed at the Chad and Stacey Evergold Studio in Indianapolis, Indiana, and it was made with the help of all these nice people and our wonderful graphics team, Thought Cafe. Thanks for watching. I'll see you later.
Okay, so I think we should move to the chapter 1 here. It's an introduction to programming. The first thing, what is the programming? Program is a list of instructions here. So think about the list of instructions that is executed by a computer call to accomplish a particular task here. So the process of the creating of instruction is programming here, right? So we think about programming that means you set up the list of instruction in order to tell the computer to execute and to bring out the particular task here. So when we think about the programming development cycle, you have the life problem, you have design, you have coding, you have testing, and you have revise here. So when you think about the cycle that means it's a loop here. So whenever you analyze problem, design, coding, testing, and revise, whenever you want to go back, you are able to go back to change the analyze, you are able to go back to change the design, or when you're testing here, you see that you need to modify something, you're able to go back to the analyze or design here, whatever it is. It's always a cycle here. So the cycle is that help you to go back anytime you want to modify the program to have the better outcome here. Okay, so when you think about the thing, if you think about, we have the example here, if you want to make the cookie here, right? You think about we want to make the cookie. Okay. Think about you want to make the cookie. So that also is the program here. So in order to make the cookie, it's the outcome here. It's the output. You think about the output. The cookie is the output here. So in order to make the cookies, that's the output. You also have the project, and you also have to do everything with the analyze. You have to design, you have the coding, testing, and device here. So think about this one. In order to make the cookie, it's the output. What do you think? What is the input you have? You have to think about the input. So in order to make the cookie, you have to think what are the input you need in order to make the cookie here. Right? So just think about the input. So everything about the figuring out the output and input, everything is in the analyze problem here. So analyze problem is that mean you have to think what is your expected output here. And from the expected output, you have to think what are the input in order to giving out the expected output here. Right? So think about the cookie here. In order to make the cookie, you have to specify how many cookies you have. So you think 10 or 5, something like that. So based on that, you have to figure it out what's the input here. So you think about you need a flour, right? Flour, you need a milk, you need chocolate chip, something like that. So you have to figure out what are the input here in order to bring out the input here, right? So that is the first step of analyze problem. Analyze problem, everything about the output here. And from the output, you're able to figure out what's the input here. Okay, that's everything about the analyze problem. So in the design program here, so once you figure out what is the output, what's the input here, you have to design program, right? So we have to think that how many flour you need, how many milk you need, how many egg you need, how many chocolate chip you need, right? So to figure out all of the things, and you have to plan that you have to go to the grocery to buy it here, right? The coding here is everything. You just stick to the design program here. So we think about you list all of the instruction here. Program is the list of instruction here. So think about you have to mix flour and milk, and you have to crack the egg, and you put you have to bake it for how long, how many how long, right? So we have the 15 or 1 hour, something like that. You just stick to the list of instruction, and the list of instruction is, or I think it's a design here. That is the coding. The coding, that means you stick into the design, you follow the instruction in the design, and you just follow it here. So when you're cooking, it's a test program. That means you can try if the cookie here is overcooked or not overcooked or something like that, or you need to put more milk, or you need to put more flour. So every time you test program here, you compare with the output here. The output is the cookie you want to bake, right? So if it's not what you expected, you have to go back to change everything. You have to go back to modify analyze. You have to go back to modify design here, right? So that everything is revised as necessary. So whenever you want to come back, it's a cycle here. So whenever you want to come back, you just come back to modify the book, so the design or analyzing here. So you move to the basic programming concept here. The basic programming concept. Normally you have you have some of the important concepts. The first one is pseudocode. Pseudocode is used to announce the logic of a computer programming here, and using the English words or phrase. Think about the pseudocode. It is not programming language. Right? You have to think that the pseudocode is not programming language. It is used in the planar logic of computer programming using the English words and phrase. But when you understanding the logic of pseudocode here, it is very easier for you to apply it into the specific programming language. So we think about when you have the pseudocode of program here, you can use it, you can convert it into the Java coding, or you can convert into the C++ coding here. Because when you understand the logic of the pseudocode, it's very easy for you to convert it into the specific programming language here. And some of the important concept is input here. You have the input. That means what are the input you need in order to bring out the expected output here. And you have variable. Variable is a value is within program, and constant also too. But it never change. It never change during the program here. Right? So we have some of the important concept here. You have pseudocode. Everything about the logic of the computer program using the English word and phrase. You have input. Right? You have the variable, and you have constant here. Okay, so here is an example of the pseudocode here. That is a pseudocode here. Program here. So we think about you have a program here. You want to compute the cost of downloading music online here. Right? So now think about, if you think about the program development cycle here, you have analyze, you have design, you have coding, and you have testing here. Right? So think about this one. This one about the example of music purchase program here, and the output. The expected output for you is that you have to figure out how much money you have to pay here. Right? You have to figure out how much money you have to pay, and that's why for this one you can set it the dollar price here. The dollar price is how much money. It's output here. Output, right? Expected output here. So how much money you have to pay? It's expected output, and you set into the variable name here. You set it into variable name. It's a dollar price here. That's the name of variable only. Right? So that is the one is expected output, right? It's expected output. So in order to figure out how much money you have to pay, you have to know how many songs you want to download. Right? You have to know how many songs you download. That is the input here. Right? That is the input here. Input here. So you see, this one everything is about analyze here. So analyze is that means you have to figure out what are the expected output, and from the expected output you also able to figure out what are the input here. Right? So think about this one. You want to know how much money you have to pay. That is dollar price, and this is the output here. So in order to figure out how much money you have to pay, you have to know how many songs you download here. Right? That is the input here. So for this one, yeah, input here is a song, and the output here is a dollar price here. Okay, So now the first step here, you know, analyze problem here is that you figure out what is output and what is input here. Now the second one, you have to design here. You have to design this one very simple, right? This program here very simple. So for the design, you just think about how can you figure out how much money you think. So we see you have the input here, and in order to figure out how much money you have the formula here, and that is the dollar price equal to 0.99 times song here. 0.99 is the money you have to pay for every song you download here. And you think about this one. This one is variable. This one variable because it's changeable. So if you download 10 songs, you have to pay the 9.9. If you download 100 songs, you have to pay for 99 here. So the variable, you think about variable, is changeable. Whenever you have a variable, it's changeable. And 0.99 here is a constant. It's not variable because it stays the same during the program. Only 0.99. So it is the price of the song, and it's always stays at 0.99 here. Right? So we think about this one. So for this one, everything here is a pseudocode here. This one is pseudocode. So basically for the pseudocode, you have 4 steps here. The first one, you have to declare variable use. And you know that in this program, you need one output is a dollar price, and you need one input is a song. That's why you have to declare the variable here, song integer, and declare dollar price as a float here. Right? So once you figure out the input and the output here, you get the input here. You have to enter how many songs you want. So we think about the input here. It can be 10 songs, it can be 15 songs, or it can be 100 songs here. Right? So based on the number of the song, based on the number of the song you already enter here, you're able to figure out how much money you have to pay based on the formula here. So this dollar price equal to 0.99. It is the price for each song you download, and the song here is the number of the song you already enter here. Right? So based on that, so think about if you enter the 10 song, you have to pay for 9.9 here, and if you enter for 100 song, you have to pay for 99 here. Okay, that is very, very simple of the pseudocode here. And now if you look on this one, I have the slide for the pseudocode introduction here. The first thing you have to understand that the pseudocode is not programming language. It is simulation of programming language, and it's during the analyzing and planning phase only, right? But the thing is that once you understand how logically pseudocode works, you will be able to work it in the every real programming language here. You can apply it into a specific programming language here. Right? So basically, for every pseudocode program here, you have 4 basic parts. The first one, you have to declare the variable use in the program here. Right? The first one you have to declare. You have to think about how many variables you have to use and what's the type variable here. Right? So think about on here. This one is the program is the same, right? So you are the owner here, and you sell about the balloon here, and the second one, you have to enter the input. You have the inputs about that. You have for the input here, you have the prompt. You have prompt, right? And they have a keyword input here. So when you have a prompt, you have to use the keyword right here. So when you have right, enter how many balloons sold today. That is the prompt to tell you that what you have to enter here. Right? So when you use the prompt here, enter how many balloons sold for today. You understand that you have to enter the number of the balloon you already sold for today. Right? So the keyword here, the keyword input, that means after this step here, you will have the slot in the memory here. And in the slot in the memory here, it's a slot name here, memory slot here, its name is a balloon here. Right? The balloon here. So that is the name of slot memory. So it's based on the number you enter, right? So if you enter the number, it is stored number 10 in the memory slot here. If you enter number 100, it store number 100 in the slot balloon here, right? So now I think this is the next one. You do with the calculation here. The third one, everything with the calculation. So it's a set revenue here. That means you have one more slot here. You have one more slot, and the slot name here is revenue. Revenue. So what is it? Revenue equal to 0.99 times the number of balloon. So it depends on the number of balloon here. So if it's number 10, the revenue here 9.9, right? But if you enter the number 100 here, it is 99 here, right? So they are changeable, they are variable here. So depend on the number of balloon you enter. Now you only have the revenue stored in the memory revenue here. So the last one is that print out the output, right? It's a print out the output here, and print out use the keyword here, right? So raw revenue is and plus the revenue. So when you see everything here is the text, everything here is the text. So whenever you have the text inside the double comma, it print out exactly the same, right? So for this one, the program is print out with raw revenue is. Now it depends on this value here, right? So if you enter the 10 balloon, the revenue here is 9.9. But if you enter the 100 here, the revenue here is 99 here. Okay, that is the simple programming of the pseudocode here. Now we think about this one, the module, the example one here. You are the sole owner. We have the balloon. Each of them is 0.99 here. That is constant. You know that not 0.99 is a constant because it's never changed during the program. That's why it's a constant here. And you have to develop a program to ask the seller to enter the how many balloon is sold for today, and from that you have to figure out the revenue. Right? So the first step here, you have to declare the variable you use, right? So we know that for this one, you need one output here. You have to figure out what is the revenue. And in order to figure out what is the revenue, you need to know how many balloons you sold. That is input here. Right? So we see this one input. And this one output here. So you see, for this one, you need one input and you need one output. That's why you have to declare for the output and input here. And you see, you declare the balloon at integer everything about 1, 2, 3, 4, something like that. And you have declared revenue at float. Floating it can be 1.2 or 3.5, something like that. Right? So that is the first part. The second one, you have to tell the user to enter the input here. For this one, you only one input here. You only need one input. That's why you have to make the prompt here. And in order to make the prompt, you have to use the keyword right here. You have to use keyword right here and enter the number of balloons sold today. That is a prompt to tell the user that he have to enter the number of balloons he sold today. So you see about this one, when you declare actually you will generate two slots here. You generate two slots in the memory. The first one, the name is the balloon here. And the second one, you have revenue here. Okay, so now after the prompt enter the number of balloons you sold today, and you enter the balloon here. So it depends on how many number you enter, right? So we think about if you enter the number 10 here, the memory balloon here now takes the value of 10. Right? So now after that, you have everything is calculation here. You set the revenue equal to 0.99 times, sorry, this one is not being balloon here. Okay, times the balloon. So it depends. If you enter the number 10 here, you have 9.9 here. Okay, and the last one, when you have 9.9 stored in the memory revenue here, the last thing is that printed out here. Yeah. So revenue is so this one now you take it from the reference from this one, and you have 9.9 here. Okay, so now if you enter the 100 here, it's not 9.9 anymore, but it is 99. So this one is print out 99 here. Okay. That is the example one. Now I move to the example two here. Now the shop owner want to change the price of balloon from the 99 here to 129 here. Right? So you see that from the 0.99 he's not able to make any profits. So he want to increase it to the 129 here. Right? So basically the program everything's the same. You need one input, you need one output. You have to declare it. You have to input here. The only difference is that you have to change the formula here. This one is not 0.99 anymore, but it's 129 here. Right? So that's the only change here. Now you move to the example 3. Now every time the shop owner want to change the price, he have to call you. He have to come to change the program here, and it make a lot of inconvenience, right? So now he asking you that you have to change the program that allow him to enter to modify the price of the balloon here. So in that case, you see, the price here is not constant anymore. It's not constant anymore, and because now it's a variable because it's changeable every time. The one time he able to enter the 0.99, the other time he able to enter 129, the other time you want able to enter the 159, something like that. Right? That is a variable now. It's not constant anymore. So in order to do that, you see, you will still have the one output here, the revenue. But now you have two inputs, not in one input anymore. Now you need the two inputs. The first one, you have to enter the number of balloon you sold, and the second one, what is the price of each balloon here? I still see you have to declare here, declare the balloon integer, and you declare the price and revenue as float here. Now you have the three variables. That's why you have the declare three variables. Now again, you have two inputs here. You have two inputs here. That's why you have the first prompt. You have to enter the number of balloon. The first one you store in the balloon here, right? The first you have balloon here. The second one is the price. So we have one more slot in the memory is the price here. Okay, so now it depends on you. So if you enter the 10 here and the price here 159, so storing the 10 in the balloon and the price here is 159. Now you do the calculation here. You set the revenue, you have the one more memory, one more slot in the memory is the revenue here. Now it depends on this one. Sorry, this one is not. This one you have to change it the price here. This one is the price here. Okay, so now it depends on the price. If you enter the price 159, and if you enter the balloon here 10 here, so we have the now we have 159 times 10, right? So we have the 15.9 here, store in the revenue. And the last one, the last thing is everything about the output here. So you print out the revenue here is a 15.9. Okay, so now we think about this one. You have to clarify the difference between the input, output. You have to clarify the difference between the constant and variable here. So constant is everything stays the same during the program, and variable is changeable, and you are able to change it. Any question for this one? Let me know. Hello?
I'm good.
Yeah, I'm good.
If you have any questions, let me know.
I'm good.
Okay. Okay, so let me go back to this one here. So basically for this program, basically for this course, this class, you are required to do simulation with the Raptor here. And you see, you can click on the Raptor here, and in that you, okay. And you have the assignment in this module. You have to download the Raptor, and you go to the Raptor download here. You have to go to the Raptor download. You are able to use it. Download Raptor. Okay, so normally I use a portable version here, so I don't have to modify anything. That's why normally I'm working with a portable version. So when working with if you want to download the portable version, you go to this one. Go to this one, you download the portable version. Yes. So is that when you download the portable version, save it here. Okay, and then click it to open it. this? Okay, so here is the interface Raptor. And again, I have to clarify the Raptor is not a programming language. It's only a tool to simulate the programming language here. But again, it's the same with the pseudocode. When you understand the logic of the pseudocode, or when you understand the logic working with the Raptor, it's very easy for you to convert it into the specific programming language here. So basically, for the Raptor program, you have start and end the program here. Right? So if you look on the left here, you have everything with the assignment, you have everything with the call, input and output here, input and output, selection and loop. And if you look on this program here, see this one, very simple program here. Think about this one, right? So we think about this one program here. You have to figure out how much money you already sold for the balloon for one day, right? So we think about this one again. If you look on this one, you have one input here, the balloon, and you have one output here, is the revenue, right? So if you look on the program here, the first thing you only have to get the input, right? You only have to get the input here. In order to do that, you just click the input and drag and drop here. Now you have the input. So when you click that, you double click that one. So when you click the double click here, the first one is the prompt. Prompt is everything to tell the user what he had to do here, right? So you tell him that how many balloon you sold for today. You put it in the double quote mark. This one is the prompt, right? This one prompt. So if you look on this one, this one is prompt here. So in order to do that, you have to store it into a variable here. You know that input here is variable balloon. So in that case, you have to store the value here. You enter into the balloon here. Okay, that is everything but the input. You got the input from the end user. So if you enter the number 10, it store the number 10 in the balloon variable here. If you enter the number 100, it stores the number 100 in the variable balloon here. Now you see, every program you only have the input, processing, and output here. Okay, input, processing, output. So for this one, you see, you only have the input, it's the number of balloon. Now the processing, that means you have to figure it out how much money you already sold it, right? So if you come back to the Raptor here, if you do everything is the processing here. You see, the next step is the processing here, right? Processing. You have set revenue equal to this one. Sorry, set revenue equal to 0.99 times the balloon here. So in the Raptor, everything you working the processing, you have to working with the assignment here. Assignment. So you click the assignment, drag and drop it here. You have to save it here. Let me save this one. Save balloon. Okay, so now you drag and drop the assignment and double click it. So now what do you have to set? You see, you have to set revenue equal to 0.99 times balloon here, right? So now we set revenue equal to 0.99. It is the price of one balloon here, and it time to how many balloon you enter. And if you time here the balloon, you see they have the transaction here. You have the transaction here. Okay, how many balloon you? So you see this one variable, right? So it depends on how many you enter. If you enter 10, it time 10 here. If you enter the 100, it time 100 here. If you enter the 15, it time 15 here. Right? So now come back to this one. You already have the input. You already have the calculation. Now the last the last thing is that you have to print out much money, right? So if you look on the printer here, sorry, if you look on the router here, everything is the output here. If you want to output, drag and drop the output, double click here. So now you have to show revenue dollar here, right? You put it here. Everything here is touch. It print out the same. Now what you have? It depends on how many balloons, right? So you have to print out its revenue here. Okay, that is very simple program here. So that is the whole program of the simple selling balloon here. So in order to run it, you have the multiple way to do it. The first one step by step here. So if you let me open it here. Okay, so now if you want to run it, you can run it step by step here. Click this one. Click this one. Now this one is input and you have prompt here. I see you have the prompt here. How many balloons you sold for today? Now it depends on you. Right? It depends on you. So if you enter the number 10 balloon, what happened? You see, they already store the number 10 into variable balloons here. Right? You see, balloon and 10 here. Store the number 10 into variable balloon. Now I click the next. Everything next one. You see, you have revenue equal to 0.99 times the balloon. You have the balloon here 10. That's why you have 0.99 times 10, and you have revenue here 9.9 here, right? So now you have the revenue 9.9. The last one is that you have to print it out. You have to tell user that your revenue is, you see, now you click on this one, sorry, and you see this one is the output here. Your revenue is 9.9 here. Okay, you got it?
Yep.
Okay, so now one thing here, if you go back to my example 2 here, he want to change it. He want to change the price of balloon from the 0.99 to the 129 here. So you look on this one, what you have to change here? If you look on the router here, what you have to change? What do you think?
Change the 0.99 to 1.29.
Yeah, the double click here, right? So you have to stop it here. You change it here, 129 here. Okay. Now for this one, I don't want to run it step by step anymore. I can run it here. Completion here. I run it here. So now this time I want to sell for 20. Okay, so now that's the program. You see, when I enter the number 20, it stores the number 20 in the variable name balloon. And after that, you do it calculation. You have revenue equal to 129 times 20. You have the 25.8 here. And the last one is the print now here. Right? That's the output here. Now, come back to the example 2. You see, this time the owner here, he want to change the price by himself. So in order to do that, you have to need one more variable. That's the price here. Right? So in that case, you see, in that case, you need one more input here. One more input here. This one, you have to enter the price each. Okay. Now, sorry. You have to store it into another variable here, right? So now this one, I put its price here. Okay. And you have to change this one. This one not 129, but now it is a price here. Okay, price here. So now you can run it. And one more thing, you can run it by the run compile here. You can run it compile here. So you see how many balloon. You have 100 here. What is the price? You have enter the 159 here. Okay, so you see is your revenue here to 159 here. Okay, and you can clear it to run it again if you want. So we have balloon, so we have say 30. Now it's a 189. Okay, and the revenue here. Okay. Any question for this?
I'm good.
Okay, good. So now we come back to this one. We come back to the program here. So basically, everything here is a pseudocode, right? Everything here is a pseudocode. Pseudocode is not programming language. It's used during the analyze and planning the design. So when you understand the logic of the pseudocode, you can easily apply it into specific programming here. You think about this one is Java code, and this one is C++ here. Everything is the same, because once you understand the logic of the pseudocode, you are able to apply it into the specific programming language here. Now we talk the first one. See that for every programming, you have the input, you have processing, and you have output here. Okay, so first thing is the data input. So in order to have that, in order to have the data input, you have to the keyword, you have to use the prompt here, right? The prompt is always tell user what he has to do, right? You tell him that here's the prompt, and in order to have the prompt, you have to use the keyword here in the right here, right? And enter the number of songs you wish to purchase today. That is the text, and it print out the prompt exactly with the text you put it here, right? So that is the prompt here, just one prompt. The second one is the keyword input the song here. So what happened? What happened here? The input song, that means you have the slot memory. You have the slot in the memory, and this slot name is a song here. Okay, so now depend on how many songs you enter, right? So if you enter the number 10 here, it store number 10 in the name song here. If you enter the number 100, it's stored in the 100 here in the variable song here. Okay, so remember, in order to get the input, you have to use the prompt with the keyword right, and after that you have to store the value into the variable here. Okay, and you have the variable and constant. You see that the variable is the name piece of memory value can change during the running program here. You think about the song. If you enter the 10, you have the 10. If you enter the 15, you have 15. They are changeable, but the value is not changed during the program. It's a constant here. You think about the price of the song is a 0.99. It never changed during the program. It's a constant here. So think about that. The variable changeable, the constant stays the same. Okay, so input or prompt, you know that always have to use a keyword right here, right? Keyword right here, enter the number, and after that, the input here store into the variable name number here, and store it into the variable here. So the same, if you want to user to get the two number, you can use the prompt here, enter the two number, and input it in number 1, input it number 2 here. And you have the naming variable. You have to sum up the rule for the naming here. The first one, all variable name must be one word only. Remember, only one word only, cannot two word. That means you cannot have this, cannot have space here. Spaces are never allowed. And variable cannot begin with the number. And thing here, you also put the name meaningful here. Right? So you think about, you have number, you can put number, you can put the name here A, B, or C, but it's better you make something more meaningful. So if you are the programmer, if you put something, the name is meaningful, it's very helpful for you to follow up the program here. You think about some of the program is very, very complicated. So always try to make the variable name more meaningful. It's very easy for you to follow up program here. The long name are allowed, but the name should be as short as possible and still, of course, short, but still be meaningful here. Okay, so here's some of the example. This one, the file, because it's one word here. This one is not, because you have space here. Right? This one is fine. This one not, because it's starting with a number. It's not. Variable one here is fine, but it's not really meaningful. Right? You have many. You have to specific on the meaningful here. Z is fine, but not meaningful. So what do you think? What's wrong with this one?
Space.
Yes, what's wrong with this one?
Begins with number.
Yeah, so what wrong with this one?
Long and not very meaningful.
Sorry?
It's long and it doesn't have much meaning.
I think it's meaningful here, right? It tell you how who jumped over the moon. I don't know. Honestly, for this one, I don't know. Okay. Okay, so now see what is really happening here. You think that when you working with the declare, right? You declare here. Actually, you will reserve one slot in the memory. We think about a declare song as integer here. Okay, so after this one, actually you reserve one slot in memory, and the memory slot here with the name of song here. It's the name of song. So after that, after the input here, after the prompt, and after the input, after the input song here. So what happened? If you enter the number 78, it reserve number 78 here. Right? If you enter the 100, it reserve 100 here. That is the song. So for this one, for this program, you have two variables. The first one is the song. So you have one slot, name the song in the memory slot here, and you have another variable $price here. It reserve one more slot in the memory here. So now depend on the number you store. You enter the number song, right? So if you have entered the number 78 here, so you have the 78 here, and after the calculation here, you see what is it here. After this step here, you see you have to set $price equal to 0.99 times song. So it will happen that after this step here, you have the $price equal to song times 0.99, right? 0.99 here is constant. The song here, it look it up in the reference of the variable name song here, and you know that it's a 78, right? 78 here. So we take out 78 and you time with the 0.99, and you have 77.22, and it's stored into the $price here. So after this step, you only have the $price is a 77.22, but you need to print it out to the end user. So in order to print it out to the end user, you have to use a where is it? You have to use the output here, right? You have to use the output here. You have to the output here. In order to do that, you have to write and $price here. Okay. Okay, so see the first one, input. The second one, processing. And the third one, output. Okay, you know that in the input, you know that how to do with the prompt by the write command, and stored into the variable by the keyword input here. For the processing, everything is the set keyword here. You know that you have to use the keyword set here, and you set the $price equal to 0.99. It is the price of the song. The song here is the number of the song you already entered, right? It's stored in the variable name here. So, and it depends how many songs you enter. So if you enter 10, take out 10 here. If you enter 100, take out 100 here. Okay. So the thing you have to remember about the data processing here in the pseudocode, you have to use the keyword set here. You have to use the keyword set, and you set $price here. You have one more slot here, $price. And it depends on how many songs. So if you have 100 here, 0.99 times 100, you have 99 here. Okay. So last step is output. Right? Last step is output. So in order to print out how much money, you have to point it to the memory slot here, and the memory slot here is the data price. The name of the memory slot is the $price, right? So that's why you have to write and you put the $price here. So after that, you print out 99 here. Okay. One more thing about variable, you have to remember that it is changeable. Right? It's changeable and it's an override here. So now, what do you think? If I set if I set x here equal to 10, now I set x here equal to 20. Now I set y here equal to x plus x here. What do you think? So what is the price of x here after this one? First one, I set x number 10. The second one, I set x number 20. Now the third one, I set y equal to x plus x here. So what do you think? What is the value of y here?
30.
Any other question? Sorry, any other answer?
Would it be 40?
Oh, wait. What's the first number?
The first number 10, the second number 20. And I said y equal to x plus x. So what is the y here?
It'd be 30. Oh, it could also be 20.
Okay, so now see, you have to remember the variable is changeable and it's override. So what happened here? I set x equal to 10. That means I have one slot here. I have one slot in the memory and the slot name is x here. Right? So first thing, I set x 10. I have 10 here. Right? Now, the second one, I set x 20. That means it will be override by 20. So it's not 10 anymore. You have 20 here. Right? 20 here. So now I set y equal to x plus x. What happened? X here, reference 20. X here, reference 20. So when I have x plus x, now I have 40 here, not 30 anymore. You got it?
Yep.
Yeah, because the variables, they are changeable and they are override here. So see, the first one, you put the number 10, it's okay. Now you set the second one 20, it changes to 20 here, not 10 anymore. So we see y equal to x, reference, it point to the x here, 20. The second one, reference, point to the 20 here. That's why y here is a 40, not 30 anymore. Okay. The same with this one. If you set the number x 45, set the number x 97 here. This one is not work anymore. It's override by this number only. Okay, the value of the 45 has been lost here. Okay, that's why you have to understand the logic of the variable here and the logic of overriding here. Okay, I don't think this one is. So the next one, we move to the operation on the data. You have the arithmetic operation. Arithmetic, everything about addition, subtraction, multiplication, division, exponentiation, and modularity. Okay, so you think about the addition. This one is simple, subtraction simple, multiplication here. This one, division here. This one, exponential here. This one. The only thing is the modular here. The modulus, that means when you divide by something, the modular is the thing you return for the remaining here. So we think about you have 14, you divide by 3, you have 4, and remaining 2 here. So the modular is everything it return for the remaining here. Okay. So now what do you think? If I have 16, I modulate for 5 here. What do you think? What do you have?
You won.
Yes, you have remaining 1 here, right? So remaining 1 here. So think about if you have 23, you modulate for 5 here. What do you have? 23. You modulate 5. What do you have?
Would it be 3?
Yes, right. It's a 3. It's 3. Okay, so actually for the modular operator, you have a lot of meaning here. So think about if you want to write program to tell if the number is the even number or odd number, right? So you see if it's odd number, when you model 2, you have 1 remaining here. And if you want to know if it's an even number, you see that when you model 2, you have 0 here. Okay. And we move to the hierarchy of the operation. You see that when you have a complex operation here, you have to do it in the order of priority here, right? So the first thing, you only have to perform any operation inside the parentheses here. The second one, you perform the exponentiation here. The third one, you do the multiplication, division, and modular from the left to the right here. And the fourth one, the last one here, anything with the addition or subtraction from the left to the right here. The thing is this one here. If we have example here, what do you think? What do you have here? You see, you have this complex operation here, and you know that you have to follow the order priority here. Right? The first thing, only everything inside the parentheses here. So for this one, you have A here. This one you have 2 here, right? It's here. Now, the next one, you have to do everything exponentiation. This one, you have exponentiation here. So this one you have 2 raised to 2, you have 4 here, right? So now I rewrite 3 times 8 here, divided by 12 plus 2 raised to 2 times 3 here, right? That's the first one. Everything with the parentheses here. The second one, you have to do everything with exponential here, right? So we see 2 raised by 2, you have 4 here, right? That's why I rewrite it 3 times 8 divided by 12 plus 4 times 3 here. Okay. Now the next one, you have to do everything with multiplication, division, right? From the left to the right. So for this one, you have 3 times 8, you have 24 here, divided by 12, plus this one, you have 4 times 3 here, you have 12 here. Right? Now, again, you have to do with the division first, right? Before the addition. This one you have 2 here, and this one you have 12 here. Last one is the addition. That's why you have 14 here. Okay, so here's the example of this one. You see everything with the parentheses first. Next one, exponentiation, and we have to do with the multiplication, division, modular from the left to the right. And last one is have to do everything with the addition and subtraction from the left to the right here. Okay, so one more thing about the data output here. So if you look back to this example of this one, right? So you have song here, you have a dollar price here. So depend. You have the prompt to tell user that enter the number of song you purchase. So if you enter number 10 here, right? Say you number 10 here, and the dollar price, you have the formula here. You have set dollar price equal to 0.9 times song here. Right? So if you enter number 10, you have 9.9 here. Now, what is input? You got the processing. The last one is the output here, right? So in order to bring out the outputs, you have to use the keyword here, right? Right? And what happened? Right, dollar price here, it reference to the dollar price and it print out 9.9 here. But you think if you look on the output 9.9 here, it not make sense, right? It's not really meaningful. So in order to have the meaningful output here, you have to annotate it here. So annotate is that means the process of you put some text here into the output to make more sense. You think about this one. If you have the test number 1 and test number 2, and you want to figure out the average here, you have average equal to test number 1 plus test number 2 and divide by 2 here. If you don't have this text here, if you don't have this text here, think about you have the test number 1 at the 60, test number 2 is 80, and you have average here 70. So after this one, you print out 70 here. It's not make sense, right? It's not make sense. It's not really meaningful. So in order to have the output more meaningful, you have to use the annotate here. So we have to write the keyword here. The text, the student average is 60, sorry, 70 here. So after this one, you will see the output is the student average is 70 here. It makes more sense for the output here. Okay, so or you can concatenate it together, right? So we see you have right here is a keyword. This one is the text here. We know everything. What's the dollar price? Dollar price link to the 9.9 here and the dollar here. So it makes more sense when you have the output. And one thing about when working the output, you have to pay attention on the formatting here. Right? Normally you have to use the space here or something like that. You see, if you write the sum up here, number 1 and number 2 is here. But if you don't have space here, see the output here very, very hard for you to follow, right? The sum of 8 here, number 1, 8, and number 2, 6 is sum, right? 14 here. It not make sense to the end user here. So instead of that, you can use the space here, space here, space here, space here, space here, space here. It makes more sense for the output here. Okay. Any question? Let me know.
I'm good.
Okay. So let me see. Actually, we will go over to. Okay, so I think that's all for today. On Thursday, I will go over the remaining of the slide on the chapter 1 here, and I will take I will take the time to working with you on the quiz and the homework assignment here. Okay, if you don't have any question, let me check the attendance here. Let's see. Dustin White here, right? Dustin White. Oh,
yeah,
right.
yeah.
Okay. Rodriguez here. Mark here.
Yep.
Okay. Mulia.
Yep, I'm here.
Okay. I had to follow it. Okay. Mulia here. Patrick and here. Peyton.
Yep. Here.
Okay. Okay, 6 of you. So if you don't have any question, you can ask the class now, and I see you guys on Thursday.
All right. Have a good day.
Sounds good.
Okay.
Yep.
Thank you.
Have a good day.